Hello everyone. In this video, we shall discuss about rational functions and some of its properties. So what are rational functions? A rational function f of x is a function of the form f of x is equal to t of x over q of x, where t of x and q of x are polynomial functions and q of x, of course, is not equal to 0 because division by 0 is not allowed. So the polynomial functions may be of equal degrees or may be of unequal degrees. So for this video, we shall focus only on rational functions where the numerator and denominators are polynomial functions of a small degree like 0, 1, 2, and 3. So for more complex rational functions, maybe you can do your own research about those examples. So for here in this video, for our examples, the following are rational functions. So first, we have f of x equal to the negative of 3 over 5 minus 2x. So observe here that the numerator is a polynomial of degree 0 or it's a constant function. And then the denominator is a polynomial of degree 1, which is a linear function. The second is f of x equals 2x plus 1 over x minus 3. So numerator is a polynomial of degree 1 and denominator is a polynomial of degree 1 as well. Okay, so third is we have f of x is equal to 3 over x squared plus 4x. So the first one, the numerator is a polynomial of degree 0 and the denominator is a polynomial of degree 2 or it is a quadratic function. So for the intercepts of rational functions, the x-intercepts of a rational function is the solution of the equation t of x over q of x equals 0. So here, if we multiply this by q of x, or if we multiply both sides of the equation by q of x, the left side will become t of x, and the right side is 0. So meaning to solve for the x-intercepts is to solve for p of x equals 0. So in other words, we need to equate the numerator of the rational function to 0. Now, in case that the numerator is a constant function, then the rational function does not have an x-intercept. Now, the y-intercept is obtained just like the other functions. We just evaluate the function f using x equals 0. Now, if we do this is equivalent to p of 0 over q of 0. So for example, let's determine the intercepts of f of x equals negative 3 over 5 minus 2x. Now, since the numerator is a constant, then the rational function doesn't have an x-intercept. But for the y-intercept, if we will substitute 0 to x, we will get negative 3 over 5 minus 2 times 0. 2 times 0 is 0, so we get negative 3 over 5 as the y-intercept. So which means the point 0 comma negative 3 over 5 is the y-intercept of the given rational function. Now, second, we have f of x is equal to 2x plus 1 over x minus 3. So for the x-intercept, we just equate the numerator, 2x plus 1 to 0, and then we solve for x. So dividing both sides here by 2, we get x is equal to negative 1 half. So that means the point negative 1 half comma 0 is an x-intercept of 2x plus 1 over x minus 3. Now for the y-intercept, so again, we evaluate f of 0. So we have 2 times 0 plus 1 over 0 minus 3. So this is going to be 1 over negative 3 or negative 1/3. So that means the y-intercept is the point 0, comma, negative 1. And then third, we have f of x equals 3 over x squared plus 4x. So again, since the numerator is a constant, then the function doesn't have an x-intercept. And then for the y-intercept, we will substitute 0 to x. So we have 3 over 0 squared plus 4 times 0. But if you notice, the denominator will just become 0. So we have 3 over 0. So that means f of 0 is undefined. So this implies that the function doesn't have a y-intercept. Now, next is the domain of rational functions. The domain of the rational function f of x equals t of x over q of x is the set of all real numbers except for the values that will make the denominator q of x equal to 0. So this means that the domain is the set of all x such that q of x is not equal to 0. So we want to avoid q of x to become 0. So that's the domain of a rational function. So for example, let's find the domain of the following rational functions. So first is f of x equals negative 3 over 5 minus 2x. So the domain here will be the set of all x such that the denominator 5 minus 2x is not equal to 0. Now, if we solve the equation 5 minus 2x equals 0, we transpose negative 2x to the other side, so we get 2 times x. And then dividing this by 2, we get x is equal to positive 5 over 2. So that means that the domain is the set of all x such that x is not equal to 5 over 2. So equivalently, we state it as all real numbers except 5 over 2, but we can also write this in interval notation format as follows. So it's negative infinity, comma, 5 over 2, close parenthesis, union, open parenthesis, 5 over 2, comma, positive infinity. Now, second is f of x equals 2x plus 1 over x minus 3. So again, we want to avoid the denominator to become 0. So x minus 3 equated to 0 would imply that x is equal to 3. So this means that the domain is the set of all x such that x is not equal to positive 3. Or in interval notation, we write it as negative infinity, comma, positive 3, close parenthesis, union, open parenthesis, positive 3, comma, positive infinity. And then third, if we have the function f of x equals 3 over x squared plus 4x. So again, we try to avoid the denominator being 0. So we equate this to 0 and solve for x. But this one is a quadratic equation. So we can factor x. And then the second factor will be x plus 4 equals 0. So equating both of these to 0 and solving for x, we will get x equals 0 and x is equal to negative 4. So which means that the domain here is the set of all x such that x is not equal to 0 and x is not equal to 4. Or in interval notation, we write this as negative infinity, comma, 0, close parenthesis, union, open parenthesis, 0, comma, 4, close parenthesis, union, open parenthesis, 4, comma, positive infinity, close parenthesis. Now, rational functions have vertical asymptotes, and these asymptotes are lines or are vertical lines wherein the graph will never touch. So the graph will just approach these vertical asymptotes, but will never touch these vertical asymptotes. But in what equation, or what is the equation of the vertical asymptotes of a given rational function? Now, asymptotes are lines that the graphs approach but do not intersect with, and the vertical asymptotes occur at the domain restriction. So, which means in our examples earlier, if the domain of this function is the set of all x such that is not equal to 5 over 2, then its vertical asymptote has equation x equals 5 over 2. And then for the second one, this one is the domain is the set of all x such that x is not equal to 3. So meaning the vertical asymptote is x equals 3. And then for the third example, 3 over x squared plus 4x, its domain is the set of all x such that x is not equal to 0 and x is not equal to 4. And therefore, there are two vertical asymptotes, and they happen to be the lines or the vertical lines x equals 0 and x equals negative 4. Now, for the range and the horizontal asymptote of rational functions, now we have to follow some rules. So the range of a rational function is the set of all real numbers except for some impossible y values. At these y values, the horizontal asymptote would occur. So given a rational function f of x equals p of x over q of x, where p of x is a polynomial function of degree n, and q of x is a polynomial function of degree m. Now, the horizontal asymptote can be obtained as follows. If the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is the line y equals 0 or the x-axis. So y equals 0 is also the x-axis. Now, if the degrees of the numerator and denominator are equal, then the horizontal asymptote is the line y equals a sub n over b sub m, where a sub n is the leading coefficient of the numerator and b sub m is the leading coefficient of the denominator. So for example, if we have a rational function that is equal to 3x plus 1 over 5x minus 4, since the degrees of the numerator and denominator are 1 and are equal, then we just get the leading coefficient of the numerator, which is 3, and the leading coefficient of the denominator, which is 5. So which means the horizontal asymptote is the line y is equal to 3 over 5. Now, in case that the degree of the numerator is higher than the degree of the denominator, then the rational function has no horizontal asymptote. But in special cases, when the degree of the numerator is equal to the degree of the denominator plus 1, then the rational function has an oblique asymptote. But we will not focus on these examples. No, we will just show one example later. But we're not supposed to graph these rational functions. So let's have examples. So let's consider the function f of x equals negative 3 over 5 minus 2x. So if you notice, the degree of the numerator is 0 and the degree of the denominator is 1. So n equals 0 and n is equal 1. N is equal to 1. So its domain, which was determined earlier, is the set of all real numbers except x equals 5 over 2. Its vertical asymptotes are vertical asymptote is the line x equals 5 over 2. And then its horizontal asymptote is the y equals 0 or x-axis because the degree of the numerator is less than the degree of the denominator. And then its range will be all real numbers except the horizontal asymptote. So all real numbers except y is equal to 0. But to be more precise or to be more exact, it is still best not to inspect the graph of the rational function in order to get the exact range of the function. So in graphing these rational functions, it's best to use a lot of points. So if the domain is the set of all real numbers except 5 over 2, then we need to use x values that are lesser than 5 over 2 and x values that are higher than 5 over 2. So in this case, we're using three values that are lesser than 5 over 2 and three x values that are higher than 5 over 2. So using these x values and substituting them into the given function, then we solve for the y values. So in here we have the point negative 2 comma negative 1/3, 0 comma negative 3 over 5, 2 comma negative 3, 4 comma 1, 6 comma 3 over 7, and 8 comma 3 over 11. So if we plot them on the Cartesian plane, we have the following. So going back here, we have negative 2 comma negative 1/3. So it's negative 2 comma negative 1/3. And then we have 0 comma negative 3 over 5. So 0 comma negative 3 over 5. And then we have 2 comma negative 3. So these are the 3 points that are located to the left of the vertical asymptote. So by the way, now the vertical asymptote occurs at x equals 5 over 2. So which means that if this is 2.5, that's 5 over 2, there must be a vertical line passing through this part of the graph. And then at the right side of the vertical asymptote, we plot the following points: 4 comma 1, 6 comma 3 over 7, and 8 comma 3 over 11. So this is 4 comma 1, and then this is the 6 comma 3 over 7, and we have 8 comma 3 over 11 somewhere here. So connecting those points, by a curve that is approaching the vertical asymptote and the horizontal asymptote, that's the graph of our rational function. So our horizontal asymptote, by the way, that is y equals 0 or the x-axis. So that's the graph of our first example. Now for the second example, we have f of x equals 2x plus 1 over x minus 3. So the domain is the set of all x uh, that are not equal to 3. So all real numbers except x equals positive 3. So the vertical asymptote will be the line having the equation x equals 3. And then since the degree of the numerator is 1 and the degree of the denominator is 1 and they are equal, so that means that the horizontal asymptote will be the quotient of the leading coefficients. So it should be y is equal to 2 over 1 or 2. So that's the horizontal asymptote. And then definitely the range will be the set of all real numbers except the horizontal asymptote. So all real numbers except y is equal to 2. Okay. And then if we have the table of values for this function, we have the following. So since the vertical asymptote is x equals 3, we will be using 3x values to the left of 3 and 3x values to the right side of 3. And then we substitute these x values into the given function to compute the values of y. So plotting these points on the Cartesian plane, we have the following. These are the points. 3, and then we have 4, 5, and 6. Now the vertical asymptote occurs at x equals 3, and the horizontal asymptote occurs at y is equal to 2. So which means that we have to connect the points, with a curve that is approaching the horizontal asymptote and the vertical asymptote. The next is the function f of x equals 3 over x squared plus 4x. So the domain of this function was determined earlier, and it's the set of all real numbers except x equals 0 and x equals negative 4. So this indicates that there will be two vertical asymptotes having the equations x equals 0 and x equals negative 4. Now for the horizontal asymptote, so since the degree of the numerator is 0 and the degree of the denominator is 2, then n is less than m. So that means that the horizontal asymptote is the x-axis or y equals 0. And the range will be all real numbers except the horizontal asymptote. But again, as I said earlier, it's still best to inspect the graph of the given function in order to determine the exact range of the given function. So for the table of values, so since we have two vertical asymptotes, we have negative 4 and 0. So if we will place negative 4 here and 0 here, so we shall use three values to the left of negative 4, three values in between negative 4 and 0, and three x values to the right side of 0. So substituting all these x values into the given function, we get the following y values. So plotting them on the Cartesian plane, we get the following points. So since we have 9 ordered pairs from our table of values, we will be having 9 points. So whenever we have a constant function over a quadratic function, the graph would be either this or it could be something like this. Okay, however, since rational functions have different types of graphs, sometimes the graph could also be like this. We have something like that, and so on. So it depends, That's why it's better to use a lot of points when graphing rational function in order to determine the exact or the closest approximation of the pattern, of the graph of the rational function. Now, if we check the range, the range is the set of all y values that is greater than 0. So because there are graphs above the x-axis, but the graph below the x-axis starts at this particular point, which is actually negative 0.75. So the exact range of this is negative infinity up to negative 0.75, union 0, comma, positive infinity. But in fact, negative 0.75 is included, so that's why it should be bracket in this case. Okay, so this is what I am telling earlier, that it's best to get or to inspect the graph of the rational function in order to get the exact range of the function. Okay, and then finally, we have the following example, f of x equals x cubed plus 4 over x squared minus 1. So the domain here is the set of all real numbers except x equals 1 and x equals negative 1. That's because if we solve for x squared minus 1 equals 0, we will factor them as x plus 1 times x minus 1. And equating both linear factors to 0, we get x equals negative 1 and x equals positive 1. So since the domain is the set of all real numbers except 1 and negative 1, the vertical asymptotes will happen at x equals 1 and x equals negative 1. So for the horizontal asymptote, so since the degree of the numerator is 3 and the degree of the denominator is 2, this indicates that n is greater than m. So in that case, there's no horizontal asymptote. Okay, however, the degree in the numerator is equal to the degree of the denominator plus 1. So in that case, this rational function has an oblique asymptote. Okay, but for the range, we need to inspect the graph. So we shall use GeoGebra in order to determine the graph of this function. So this is the graph using GeoGebra, and observe that the oblique asymptote happens at the following. So this is considered an oblique asymptote. So the domain here is the set of all real numbers except the vertical asymptote at negative 1 and positive 1. But the range is the set of all real numbers. So that ends our discussion of rational functions, and I hope that you learned about its basic properties. And please do not forget to subscribe to my channel, and thank you for listening.